Okay, there you go. So there is one of the problems that we actually have in our assignments that look like that, right? So we have a pulley, and then this actually is connected with another pulley over here. All right, and we know that these two pulleys basically have the same mass and then the same radius, and we know that G is acting downward, and we would like to basically find the acceleration of that point, and I'm gonna call that G2. All right. How do you guys think we can solve this problem?
And we draw a free body diagram for each pulley for each.
Exactly.
And we solve for the momentum and for the summation of forces.
Momentum, right? So we want to be careful here. We're not. There's no momentums here, right? Inertial accelerations is what we're going to put on the acceleration figures, right? Inertial accelerations are not called momentum. Okay, so if I were to actually draw a free body diagram on here, so I'm just gonna like quickly kind of put it right. So I know that this guy is my normal, right? And I'm going to have here, I'm going to have mg like that on this guy, and then here I'm going to have also mg the same, and we're going to have also a tension, right? So the tension is going to be applied on this guy like that and on this guy like that, right? So these are the forces. So we have a tension in the cable, we have mg on a larger one, and then we have mg here, and then we have n. So let us let us actually draw also the acceleration diagrams, and I'm just going to do it here. So how do you think the acceleration diagram would actually look like on this guy?
بس في عليه الفا اي الفا ما عنده اي جي.
IG alpha, exactly. So this guy is only IG alpha. How about the bottom one?
We have AB going downward.
Exactly, we have M AG2, right? And then what else? Is it also rotating?
Yes, we have IG alpha.
Yeah.
Exactly, we have this guy, right? We have IG, right? Alpha 2, maheke, so they have different angular accelerations, right? Okay, so very good. So let us see right now is how many unknowns do I have in total?
4.
Okay, let us count them, right? So we have the normal reaction with the wall, right? So this guy is N. And then I have the tension, right? What else? I have alpha 1. And then I have alpha 2. 4, right? Am I missing anything else? I'm missing AG2.
Still AG.
Exactly, AG2. So how many unknowns do I have? 1, 2, 3, 4. I have 5 unknowns. So essentially, I have to have 5 independent equations, and then I'll be able to solve that system, and then I'll be able to get all of them, right? What are the equations that we have? What might be the 5 equations? Well, I know on this guy I can sum the forces in the vertical direction, and then that is one equation, right? Let us do this. So I'm gonna have N minus mg minus t is equal to 0, right? So I know N will be equal to mg plus t. So that is my first equation. And then I have the torques, right? And then we said it doesn't really matter where you sum the torques on this guy. You can sum it here about this point, whatever point that you choose, as long as you use the same point on both of them. I think it's easier if we actually sum the moments here, right? Because we can have another independent equation that is primarily in t and then alpha, right? So if I sum the moments about point G1 and I use my clockwise direction to be the positive direction, then I'm gonna end up with what? T multiplied by R, right, is gonna be equal to IG multiplied by alpha 1, right? So that is my equation number 2, right? This guy is your equation 1. And we need 3 more equations, right? So I know I can sum the forces on this guy vertically, right? So summing the forces on here bottom pulley, and I'm gonna end up with T minus mg is equal to minus m ag2, right? So simply summing the forces on this guy in the vertical direction, I'm going to get T minus mg, right, is equal to minus m ag2. And I still also have to sum the torques, and probably it's easier if I do it about here, because that way I can cancel the moment arm for mg and also the moment arm for mag2, right? So sum the moment about point g2, and I'm going to end up with T multiplied by r is equal to ig alpha 2, right? So here now we've basically developed 4 equations, right? Can someone tell me what is the 5th equation?
We can find the acceleration of ag2 with respect to the point with horizontally with the rope,
right,
that have an acceleration 0.
Okay, bravo. So this point has an acceleration 0, you said?
Yes.
Do you
Because
guys agree?
نو عند الاكسلريشن مثل البوينت اللي فوق على التي الثانيه عم
Bravo.
بيبرم.
Exactly. So that point actually has the same acceleration as that point, because this is a rope, right? That rope is falling down, right? So every point here is accelerating downward with the acceleration of this point, right? What is the acceleration? What is the vertical acceleration of that point? The vertical, right?
alpha 1.
Exactly, right? So the acceleration of that point is going to be alpha 1 r. Okay? Now, what is the acceleration of point G2? If we use that point, right? So we can just apply theory right now. If we actually call that point P, okay, I can say AG2 is equal to AP, right? Plus alpha cross R G2 with respect to P minus omega squared. But here we're talking about the case where you just released it, right?
Yeah.
In that case, what do you think AG2 is going to be? I think this guy is going to be equal to alpha 1R. Okay. How about the second one? I believe it will also be equal to plus alpha 2R. Right? And then this is my 5th equation. So the 5th equation is basically, I got the first acceleration of that point, and then here, because this guy is also kind of, falling downward, then this guy is actually have some acceleration with respect to that point as a result of this alpha 2.
Doctor, may you repeat, please? I didn't understand why isn't it like...
Yeah, sure, no problem. So we said we need one more equation, and we know that equation has to be from kinematics, right? We can kind of relate the acceleration of that point with alpha 1 and then alpha 2. And the way we did that is we set the acceleration of point G2 is equal to the acceleration of that point P, because that point P also belongs to the same rigid body. So AG2 is equal to AP plus alpha 2, the angular acceleration for that rigid body, alpha 2 cross RG2 with respect to P. Right? You agree? So this is what we said. And I know the acceleration of point P is actually equal to alpha 1R. So here I can certainly put that in the vertical direction, and I can, put a frame. But here, if I look at the vertical component, I know for sure that AP will be equal to alpha 1R, right? And I know this guy, because alpha 2 is in that direction, and this guy is going to be alpha 2 cross RGP2 will actually give you alpha 2 times R. Or we can actually do the cross product if you guys want. But here, I think you should be able to quickly see that happening here, because that point AP will definitely have the acceleration of that point, which is alpha R. Right now you are here. Now how about here? So if you have a rigid body, that rigid body is basically having this angular acceleration alpha, and we know the acceleration of our reference point P. Then it will simply be alpha cross RP or R, whatever G with respect to P, right? And now AG2 is going to be the summation of these two accelerations. Does it make sense, or should I?
Yes.
Doctor, why didn't we use the omega squared times R in the formula?
Yes, the only reason why we didn't use omega squared times R is because we are calculating now, we are solving that system basically as soon as we release it. Right, so we're not finding, for example, the acceleration of point G2 after some time t, right? We're finding
so omega is 0.
Omega is 0, exactly. So at the release. Okay. And by the way, guys, in that problem, the question is we need to find here, as soon as we release it, we need to find the normal force, like find n. This is a question, right? So as soon as you release the pulleys, we need to find the normal force. Normal force that is actually holding this guy up to the wall. So what we'll just do, basically, we'll just solve that system, and then we should be, we'll be able to get all of them. Okay, guys. So now we have 5 equations, 5 unknowns, and I think the easiest way is to relate the tensions, right? So from this equation and then that equation, okay, they have the same IG and then the same radius, right? So equation 3, equation 4, and then from equation 4, you guys can tell that alpha 1 actually will be equal to alpha 2, okay? So, or if you take the tension, it's going to be equal to IG alpha 1 over R, and then from here is equal to IG alpha 2 over R. So if this has had different moment of inertias and then different radiuses, then you can find the relationship between alpha 1 and alpha 2. In that case, alpha 1 is going to be equal to alpha 2, okay? And if alpha 1 is equal to alpha 2, I can actually now use the 5th equation, and then I can say here AG is going to be equal to 2, let's call it equal to alpha, so they have the same angular acceleration, the value of it, right? So the AG is equal to 2 alpha R, right? And now from here, what can I solve for? How do you think I'm going to be able to proceed from here?
We get the tension from the second equation, and then we get N.
Exactly, right? So from this equation, right? Well, here, these 2 equations, basically, they allowed me to relate alpha. So alphas are equal. And then from here, we have AG is equal to alpha R, or to 2 alpha R, right? So from that equation, I can relate the tension and then alpha, right? And then I can use either this and that right now, and then I can actually solve for AG. And when I solve for AG, I can, or I can basically solve for a tension, and I can plug it here. But let's see, in these problems, there is no, no matter how you do it, ultimately you are going to be able to solve it, because it's a system of equations, and you will be able to basically, by kind of elimination, you'll be able to basically solve it, right? So we said here AG2, okay, is equal to 2 alpha R, right? And from equation 3, we know T is going to be T minus mg is equal to minus mag2. So T is equal to mg minus mag2, which is equal to 2 alpha R. So that is one equation. And from before, we said T times R is equal to IG alpha, right? And that guy was alpha 1, but because we know alpha 1 is equal to alpha IG times alpha. So I can say that T is equal to IG alpha over R. So if I actually take this and then put it here, I'll be able to solve for alpha, right? So IG alpha over R is equal to mg minus m2 alpha R. So here we're solving for the angular acceleration. So alpha IG over R plus 2mr is equal to mg, right? And here, if you multiply by R, you are going to get, and then notice here, you will get always the same units, right? 2mr squared, which is the unit of the moment of inertia, and then this guy is going to be equal to mgr. So alpha is equal to mgr divided by IG plus 2mr squared. Then I can solve for then I can kind of get my T back, right? So T is equal to IG alpha over R. So, oops. So T is equal to IG alpha over R, and I've already solved for alpha. So just multiply this guy by IG over R. So dividing R, you're going to end up with IG. So IG multiplied by mg divided by IG plus 2mr squared, right? So I think this is going to be our tension. Okay, and that makes sense. Why? Because IG divided by IG plus 2mr squared is unitless. Okay, so we only end up with mg, which is unit of the tension. So now we have the tension. We can basically solve for the normal, and then we know the normal is going to be equal to T plus mg, which is basically mg 1 plus IG divided by IG plus 2mr squared. Okay, guys, so so that is really it. And again, the approach that I did here is, you know, you can use any method to solve the system, right? Here, what is really important is that to recognize the equations that you have, right? So that is what we did. So basically, we, on the first block, right, or the first pulley, we sum the forces in a vertical direction, and then we sum the torques. And then on the second pulley, we did the same thing. And then the last equation, basically, we used the kinematics, right? And from the torque equations, basically, we realized that alpha is equal to alpha 1 is equal to alpha 2. We combined these, and then we got Ag2 to be equal to 2 alpha r, where we assumed alpha 1 is equal to alpha 2 is equal to alpha. And after solving Ag2, we plug it back into the equation that would allow me to relate Ag2 with the tension, right? So the tension is going to be equal to this guy, and now this guy is a function of alpha. And this guy or this guy, either of those are the function of alpha, so we can use this to basically solve for the tension. And then once we had a tension, we solved for the normal force. Does this make sense, guys? It's a pretty basic, right? But you know, you just have to understand, you know, the layout and then how you really think about it.
Doctor,
Yes.
can you please repeat how we got alpha 2r and Ag2?
Yes, you mean here?
Yes, alpha 2r.
Yeah, sure. So here we need an equation that would allow us to relate the acceleration of G2, right, with alpha 1 and then alpha 2. And we know from kinematics, right, that the acceleration of this point can be related to the acceleration of this point because that point belongs to the same rigid body. And then we can always write Ag2 is equal to AP plus alpha 2 cross Rg2 respectively, right? But how do you know the acceleration of point P? We know acceleration. We know point P basically belongs to the rope, right? And the rope is going down vertically, and the acceleration of this point has to be equal to the acceleration of that point, and then that point belongs to that rigid body, and the acceleration of that point is equal to alpha r, right? Because that pulley is rotating about the center. So the acceleration of this point will be alpha r in that direction, and it will be actually equal to omega squared in that direction. Okay, but since we're only considering the vertical component, then I know point P will have this acceleration which is equal to alpha 1 times r, right? And then you can simply relate the acceleration of that point with the acceleration of point P. Okay, so you know, maybe you can give it some thought as well, and I think that will make sense to you, you know, after you kind of, you know, think about it again. And then here I just solved for you guys, but if you give it some thought, you'll see that this definitely makes sense.
Okay, thank you.
Okay. All right, guys. So let us actually solve another problem that I also have here, which is there's actually a couple of problems that I wanted to solve. Let us actually solve the problem that we were asked last time regarding the inclined card, basically, right? And I'm just going to show you the problem again, and that is from the last chapter. Okay, there you go. So this is a problem that I think someone asked me that question last time. Is we have this uniform crate which has a mass of 50 kilograms, and then it rests on this cart having an inclined surface of 15 degrees. We need to find the smallest acceleration that the crate will either tip or slip relative to the cart, right? And we said we can solve for one acceleration that will create the slip, and then we'll rewrite that, and then we can solve another equation that would allow me to solve for the acceleration that would cause it to slip. And then I guess the confusion was here that x was equal to 0.25, and then, you know, how come we're basically solving for x? And if you actually see the last line here, they tell you that x is less than 0.3. So in that problem, basically, let us actually solve this problem using our method, and then we're going to see that what we have learned is basically essentially the same thing that they have done here. But here basically they took kind of a shortcut, which you don't really have to do as well. Okay, so let us draw a free body diagram on here. Okay, so the free body diagram, we know it's gonna look like that, right? So we have, this is the crate, right? And what are, okay, let me stop this so we can see what's going on. Okay, so this guy here, and then that guy has to be equal to, all right, so we have this guy is kind of 15 degrees. And then this is your center of gravity. Okay, can someone tell me what are the forces applied on here? So we know, yeah, so we have
the normal, the weight, and F.
Exactly. So how does the normal look like? So the normal, like I said last time, always has to be, right, perpendicular, exactly, to the surface, right? And then I have the friction. So how does the friction look like? So the friction actually has to be like that as well, right? Right. So that is your friction force, and then here we have the weight, and this weight is going to look like that. And how about on the right figure? We have only the acceleration, right? And then the acceleration has to be horizontal in this case, and that acceleration is equal to m times a, and then I'm simply going to keep it as a. All right, so we need to find the smallest acceleration so that this guy wouldn't slip, right? How do you address that? So the smallest acceleration when this guy is about to slip, then I know F has to be equal to how much?
US times n.
US times n, exactly. So that guy would be on the verge of slipping, right? So how do we solve that? So first of all, let us, what we'll do is we're gonna count our knowns, our unknowns, and then we're gonna count our equations, right? How many unknowns do I have if F was equal to mu S times n? So the unknowns are going to be simply n, right? And then what else?
A.
A, exactly, right? So the unknowns are going to be n and then a, right? And from here, basically, I will be able to, how many equations do I have?
Or 3. The
Three.
sum of forces in the two directions and the moment with IGF. It's not rotating.
It's okay, it's not rotating. In this case, basically, we have two unknowns. So all we do basically is only two equations, right? In that case, the moment will actually be kind of redundant, right? It wouldn't help me to do anything over here, right? So if I were simply going to get the acceleration for this guy when s is equal to n, right? So now I'm relating f to n. In that case, basically, I only need two equations, right? Because I have two unknowns, and then I just need two equations. And the equations are simply summing the forces in the vertical direction. In that case, I'm going to end up with what, right? If that angle is 15 degrees, then that angle right there is, let's actually keep theta, I call it theta, and then this angle right there is going to be how much? Theta, right? So if I'm summing the forces in a vertical direction, I'm going to end up with what? N. So N is going to be multiplied by cosine theta plus F sine theta minus mg is going to be equal to 0, right? And now I know F is equal to mu S times N, so I'm going to write it like that. So N cosine theta plus mu S N sine theta minus mg is equal to 0, or basically N cosine theta plus mu S sine theta is actually equal to mg, and then basically here you directly are solving for n. Right now, if I want to sum the forces in the horizontal direction, what am I gonna end up with? So again, I'm gonna end up with, can someone tell me what are the forces in horizontal direction going to the left?
F cosine theta minus n sine theta.
Exactly, so it's gonna be F cosine theta minus n sine theta is gonna be equal to MA. So I'm just kind of shifting to using the capital letter, right? So here we know F is gonna be equal to mu S times N. So mu S n cosine theta minus n sine theta is equal to MA. And here I know N US cosine theta minus sine theta is equal to MA. And from here, basically, I know what N is. I can directly solve for the acceleration, right? So from the vertical forces, I can solve for the normal force. And from the left side, I can essentially solve for the acceleration. And the reason, guys, here why we are able to solve for the acceleration is because we put what is the maximum value for F, right? So we are relating F to the normal force, right? And the normal force can be related to mg as well. So basically, the system of N and F can be related to mg. And here we are essentially able to solve for that acceleration. So how do I get N is, like I said, from here. So mg, right, divided by that. So ultimately, you're going to have US cosine theta minus sine theta divided by this guy, right? Cosine theta plus US sine theta is equal to MA. And then I can knock down the M. And this is going to be my acceleration, right? So does it make sense, guys? So this is acceleration that would what? So this is the smallest acceleration, right, that you can have before this guy can slip. If you increase the acceleration more than that, then what is going to happen? Then basically, let's say you actually know the acceleration. We're solving for the acceleration because we know the force, right? But let's say you actually you have the acceleration. If you have the acceleration, then what? Then you can actually solve for the friction force, and then you can test if that is slipping or not slipping, right? So here we're solving for the acceleration at the verge of slipping, right? And then this is what we're doing. Okay, so in the book basically does that exactly. And then if you actually solve for this acceleration, which is g multiplied by this, you're gonna get this value, which is what we had, which is 2.01, right? So if you plug the numbers here, you're gonna get 2.01. And what the book is doing is, at that acceleration, basically, they test to see if it's tipping, right? And then if it's not tipping, then they say, that's fine, you're not tipping. And how does they test for tipping? So now, what you can actually use is, you can sum the moments about that point here, and then let us actually call that point O. If you sum the moments about point O, right, what you are actually going to be able to do is you are going to solve for one more unknown beside the normal force. And then let's actually kind of see what happens if you actually draw the moment about point O. Here, the normal force, when you are summing the forces, it doesn't really matter where the normal force is, right? Because the angle is not going to change. So if you're summing the force in the vertical direction, no matter what N is, we are simply looking at the vertical component of the normal force. So here, obviously, we're multiplying M by cosine theta and then M by sine theta. But if you are actually summing the moments, then it would matter actually where N is along that surface, right? So if you actually use the summation of the moments, then you will actually be able to solve for one more unknown, which is the position of N with respect to O. So you can actually create another here variable, right? And then you can actually call that guy X, right? And if you sum for the moments, if you solve for X, if X is here based on this acceleration, then obviously this guy is not tipping, right? Does that make sense? So this is exactly what they are doing in the solution. So they've introduced another variable here, right? X, right? And then you can here sum the moments about point O. And if I sum the moments about point O, what am I going to get? So I think here the easiest way is to essentially project about looking the forces about looking at the moment R. So essentially projecting the forces on these axes, right? So if this guy is 15 degrees, then you know this guy has to be equal to theta, right? And this guy here has to be equal to if this guy is theta, then that guy is theta, right? And from the figure, we know that we have 0.6 and then 0.1. We know that this guy is here 0.6, and then we know this value from here to here is actually 1. Okay, can someone tell me what happens if I sum the moments about 0.0? What is the moment for mg?
You can say that it's mg cosine theta times the distance in a half of in a 0.3.
Exactly, right? So if I sum the moment of mg is going to be mg cosine theta multiplied by 0.3, right? How about else? Do I have any other moments here?
The other component of mg in mg sine theta.
Exactly. So now that force actually has 2 components, right? So it has one component of that force, which is, so I can basically decompose that force into this component, and then we have another component, right? So this force has a component in that direction and then a component in that direction. So doing the clockwise, this component, mg cosine theta, is in a positive direction. That is why I have a plus. How about the other component? So I have minus mg sine theta multiplied by how much?
0.5.
0.5.
Exactly, by 0.5. Very good. Okay, so now we're done with that. What is the other thing that I have right now going on? I have n. Okay.
Minus m times
Exactly. Minus n multiplied by how much?
x. Is it x?
Exactly, x. So hello, we are introducing a new variable because we can technically solve for x, right? And I'll show you why. So we can have minus an x, right? And that's it. And on the right side, what do I have?
طبعا MA.
Again, MA basically has 2 components, right? It has component downward and then component in that direction. Okay? So, and this angle is theta, right? It's going to be equal to how much? MA, can someone tell me?
MA cosine theta times 0.5.
Exactly. Is it in a
And-
positive? Okay, مظبوط. Plus what?
MA sine theta times 0.3.
Bravo, very well. Okay. Okay, guys. So what I want to do here, I want to explain to you guys شو عم بيعمل, how the solution is being solved and how we can solve it. We can, we can solve it in so many ways, right? And I think what you guys know in our course, you really can solve it in ways. So what the book is doing basically is you are now we can, if you introduce x, hell acceleration basically, what we used earlier, right? What we assumed at tipping, what did we assume x is equal to?
0.
We assume x is equal to 0, and then we solve for the acceleration that causes tipping, right?
Yes.
Okay.
Okay.
What the book is doing is basically they are getting this acceleration from this minimum acceleration, right? And then they solve for x. If x is within the range, then it's not tipping, right? But if x is greater than 0.3, then what happens? It means that it is tipping.
دكتور مثلا x إذا كان 0.2 شو معناتها؟
You tell me. So based on, so أنت هون you specify the acceleration. So if you specify the acceleration based on acceleration that we solve at the verge of slipping, and then x is equal to 0.2, can someone tell me what would that mean?
يعني
sliding.
No.
لا,
So,
it's smaller than 0.3.
Which means that it's not tipping. Right?
Yes.
So your normal is here, right? It's not tipping. Okay? It's tipping then if the normal force is basically somewhere here, right? Or beyond. Okay? It means that you're way more than the acceleration needed to basically tip the block instantly as soon as you apply the force. Okay, so what we have been doing, for example, in one of the problems that we solve in our examples, basically we just had like something flat and we're kind of pulling it like that. So we assume tipping, basically we said the normal is basically here, and we summed them out about that point, and then we said it's tipping, right? This is basically the same thing. So we can assume this guy is 0, and then you can solve for the acceleration for tipping. Okay? So you're gonna have one let's call it AT for tipping. So you solve basically AT, and then we compare it basically. So we have AT, and then we have the previous A for slipping, right? And basically you choose the smallest one. Okay? If the acceleration for sliding is less than the acceleration of tipping, then this would be the least, right? If the acceleration for tipping is less than that, then basically it will tip before it slips, right?
Why did you set X for 0, not 0.3?
Because I'm measuring X from this point, not from the center.
Okay.
Right? X is basically measured like that, is a vector from here to here, right? Yeah, so this is actually, I have another figure for that, right? So basically X is measured like that, right? Okay, and then you're solving for this value, and then if it's 0, then it means basically, I'm sorry, if it's greater than 0.3. So X, I'm sorry, X is a total value, is the absolute value between this line and that line, right? If X is greater than 0.3, it means that you're somewhere here, right? Which means you are basically slipping, or I'm sorry, tipping. Okay, guys, so just to kind of recap on last time, right? So this is what we did basically. We introduced this variable, right? And we can basically, so for the acceleration that would cause this guy to slip, we can solve for X, right? And if X is greater than 0.3, right, then it means that this block will basically be tipping, right? The other way would be is you assume X to be 0, right? So the normal force is right here, and then you can solve for the acceleration that would cause this guy to tip. So you either set X to be equal to 0 and then find the tipping acceleration, or you use the sliding acceleration, whatever acceleration you have, and then you check if X is greater than 0.3. And if X is greater than 0.3, it means that you have already, you're already tipping.
And doctor, if X is less than 0.3, it means it's slipping?
No, if
or
X
it's not
is
moving.
it means it's not tipping. That's it, right? If X is less than 0.3, so we already, you here, like, so when you specify head acceleration on it, and you make that acceleration as equal to the slipping acceleration, or at the verge of slipping, you know, it means at the verge of slipping, it means you're not slipping, so this is fine. Then you want to test if it's tipping, right? If it's tipping, basically you solve for X, right? And if X is you know, less than 0.3, or you know, anywhere in the middle, basically it means that this is not tipping, right? Because your normal force is, you know, somewhere is like, you know, somewhere here, right? Is, you know, it could be here or there, right? If N is here, basically it means you have enough support. Basically, this is not going to tip. But if N is all the way here, meaning X is greater than 0.3, it means that it would be slipping. I'm sorry, it would be tipping.
Okay. So we cannot check if it's slipping. It's slipping after the acceleration, when the acceleration increases, the one we got before.
Yes. So we actually have 1 minute left. So I'm gonna close, and then we're gonna start again, and then so we can reset the lecture.